All right. Hi, everyone. Welcome back. So, this is again my personal quest of going through this book, which is the CLRS Introduction to Algorithms. And last time we got to the technique of divide and conquer. So, technique of problem solving called divide and conquer, where to solve larger problems, what we do is we try to break them up into problems of smaller size, but the same kind of problem. And then solving those smaller sized problems, and then finding a way of putting together the solutions to those smaller problems to form the solution to the larger problem. So we looked at a specific case of this divide and conquer approach, which was the merge sort algorithm. And we didn't quite get to merge sorting. We were just looking at merging. Now we talked about we mentioned what a recursive algorithm was, and we said that divide and conquer approach usually consists of recursive algorithms, where a recursive algorithm is an algorithm that essentially calls itself. It calls the same process but on a smaller subproblem. And once those smaller subproblems are solved, there's a process by which the solutions of those smaller subproblems are combined to form the solution of the larger problem. Okay, so you can see that here in the book. Clearly, they say divide. So again, that's dividing into smaller sized things, conquer, solve them, combine, put them together to form the solution to the larger thing. So we saw the pseudocode here, and this was the pseudocode for merging. So we were merging elements in in this array called A. So we divided A into, so we're assuming that we're dividing this array A into two subarrays, and one of them had size q minus p plus 1, the other one had size r minus q. So I'm just going to go over the image of this one more time quickly. Let's see. Here we are. So we have some array 1, 3, negative 1, 0, 7. Now PQR. So I paid closer attention to how this pseudocode is defined in the book, and PQR are said to be indices. So this is all, each one of them is an index into the array. Now, my understanding when I see this statement, what I'm thinking is P, Q, and R have to be they have to be an index into array. Like R cannot point to the place in memory after the end. So P could be either one of them could be 1 or 2 or 3 or 4 or 5. That's all they can be. These are my indices into the array. Like none of them can be 6. Then the other constraint that the book mentions is that P can be less than or equal to Q, but Q has to be strictly less than R. Now, what does this mean? This means in our case, suppose this is my P right here. And the same one is my Q. In other words, one of my subarrays is just this array 1. And then I can let R be 5, in which the second one will be 3, negative 1, 0, 7. And that's all good and fine. Now, what is the size of this left array? Well, it has one element. That is Q minus P plus 1, right? Because Q minus P is 0. They're both pointing to the element 1. But 0 plus 1 gives me 1, and that's the size of my array, so it matches what the book wants. How many elements do I have here? I have 4 elements. So this is my R here. And that is exactly R minus Q. 4 elements, right? Q is 1, R is 5, R minus Q is 4. Now you might say, how come I have a plus 1 here? I don't have a plus 1 here. And the reason we do not have a plus 1 here is because we do not want to count the 1, the thing Q is pointing to. We do not want to count the 1 as part of this array. 1 is part of the left array. 1 is not part of the right array. If I did a plus 1 here, then I'm also including in that count the element at which q is for which q is an index. I don't want to include that element. That element is in the left subarray. So that's why there's no +1 here. Okay, so that's fine. That actually matches the specification of the pseudocode, the algorithm, and then we can go ahead with the merging. But imagine this scenario. Imagine that the array I want to run merge on is this. It's an edge case. This is it. So, okay, P, Q, and R have to be indices into the array. Remember that. So they can only be one thing. They can be just one. So 1 is my P, it's my Q, it's my R. That's it. But the specification also said that P has to be less than or equal to Q, but strictly less than R. And that is not the case here. That cannot be the case here because P and Q are 1. For them to be strictly less than R, R would have to be at least 2. But we do not have 2. Why not? Because 2 is not an index into our array. Our array doesn't have 2 elements. So in this case, again, if I am interpreting the pseudocode correctly, and I very well might not be, this is my first pass at it, but if I'm interpreting it correctly, this specific edge case might not be specified by the pseudocode. So when we actually write the code, we might have, like, on top of the code, an edge case where we might say if the size of my array is less than or equal to 1, just don't do anything. That's it. We might have an edge case like this. Okay, so this is just a side note. We'll get there. We'll cross that bridge when we get there. All right, back here. So just let's quickly go over the pseudocode again. So left subarray, right subarray, copy them into their own arrays, right? Now notice there's this extra, the arrays are one more than what they need to be in size. See, n+1, n1, and subscript 1 plus 1, and subscript 2 plus 1. What was that plus 1 for? The plus 1 was for these sentinels that we said we're going to toss in there. Okay. So lines 4, 5, 6, and 7, all they did was they copied the elements from this array A, the appropriate elements, into the left subarray and into the right subarray. Once that copying is done, then we put in our sentinels, and then we start the merging process. And the merging process essentially puts the elements from the left and right subarrays back into A, but this time in their correct order. All right, so hopefully this makes sense. There was a nice visualization here. I hope you took a look at it. And let's see. And there's merge sort. Okay, so what we're going to do now is we're going to start up Python and we're going to try and implement this, because it's fantastic when you understand something theoretically, but there's a certain click that happens when you actually implement it, because it just happens that in the real world, when you're doing things in the real world, quite often there are problems that arise and you want to be able to solve them. So let's take a stab at it. So we'll make a new Python file here. Call this, go to CS, we'll go CLRS, and we'll call this merge sort py. Okay, so we'll define a routine called merge. Merge will take A, it will take P, Q, and R. Okay. So we'll talk about cleaning up the function, writing some docstring, etc. later. I personally don't like to work that way. I don't like writing tests first or comments first. I like putting down my function, maybe running it against a couple of test cases, seeing that it works. And once I'm relatively confident that it works, I'll write a docstring, I'll write some test cases, then I'll start going through the formal process. Okay. So what do we want here? What we want is to create 2 new arrays of the specific size, right? Well, what we can do is we can do the following. We could say this. So let's take we'll call this L and R. L and R will be This will be my left subarray. This will be my right subarray. Now, how do I want to define these? These need to be a copy, right? These are new subarrays. These are new subarrays that we need to make. They're new containers. So I need to somehow copy A from these many elements of A. I need to copy over. So how can we do that? Well, we can say let's take A. And in case you don't know how to do this, actually, you can always look up online. That's what this is for. Let's go to Google and let's ask Google how to copy a list. And Google says you can slice it like this. You can use the built-in list function. There we go. So we can just use the built-in list function, I suppose. Or we can import copy and copy it this way. This is slower than list because it has to find out the data type. Okay. Let's try to use this list method here. So I'm going to say this is going to be a list of A starting from P going to Q minus P plus 1. So now I've put down some indices, right? Now you might not be sure whether you're not confident whether these indices you've put in are correct or not. Okay, fine. We can always check, right? Imagine P, let's go back here to our example. Now imagine that, here we are. So imagine P is 0, right? So in CLRS, remember indexing starts from 1, but in code we're starting it from 0. So imagine now P is 0 and Q is 1. So P is pointing to this element, Q is pointing to this element. So I want my left subarray to be just the elements 1, 3. So let's see if that matches up. So if P is 0 and Q is 1, then what do I get? I get 1 minus 0, that's 1, plus 1, that's 2. Now in Python, remember, when we're doing these list slices, the rightmost index is non-inclusive. So even though this statement here says 2, we're going to go only up to element at index 1, which is 3. So that's all good. That's what we want. Now the right subarray will give me the list of A, and we can go from Q to R. So now, again, let's suppose you're not sure, right? You're just not sure what you're doing here. No problem. So let's do this. Just to make sure things work, let's try and return LNR. Save this, and we'll try to run. And we'll try to run this. So let me go to the folder. There it is. Let's start up Python. We'll start it in interactive mode so we can use our function here. Now, let's define our array. We'll use the same example as I've drawn out here, just so we can reference 1, 3, minus 1, 0, 7. There we go. Now I'm going to try and call the method merge. -1, 0, 7. Yeah. Notice one thing. Remember, it's crucial that the left and right subarrays are sorted. That's by assumption of merging. And so notice that 1, 3 is sorted, and -1, 0, 7 is sorted. So that constraint holds. So now I can say merge A. P will be, remember, P, Q, and R are indices into the array. P is where I want to start the merging from. I want to start from the beginning. Okay. Q. What is Q? Q in our case is 2. Or excuse me, it's 1. It's 1. And what is R? R is the last element of my array, right? How many, the index into the last element. How many elements do I have? I have 5 elements. 0, 1, 0, 1, 2, 3, 4 is my index into the last element. I say merge, and look what I get. I get 1, 3, 3, negative 1, 0. So clearly, we have some kind of indexing issue. Why do we have an indexing issue? The reason we have an indexing issue is because notice that 3 is both in my left subarray and in my right subarray, and 7 is completely ignored. Why is 7 completely ignored? 7 is completely ignored because remember that we just said Python list slices do not include this last index. So the last index was the index into my array. So that didn't get included. So what do I need to do here? Well, I could say r plus 1. Let's see if that takes care of it. So let me restart this whole thing. Let's see. And we'll again define same a, and we'll call merge on it. All right. So now the 7 is included. The program does look at it. Now we need to take care of this 3. What's going on with 3? Let's look at the example here. So P was 0, Q was 1. From 0, 1 minus 0 plus 1, that's 2. So that's all good. Now remember that Q is still 1, right? But Q is still 1, but I want to Q, that Qth element itself has been put in the left subarray. So I don't want to start from Q. I actually want to start from Q plus 1. This. Okay? I want to start from Q plus 1. A, merge it. There we go. Let's try a different example. Let's say A is negative 4, negative 2, 0. And then we'll say 0, 1, 2, 3. Now I want to merge A. I want to start from 0. I want my Q to be what? So 0, 1, let's say 2, the second element. And then I want the R to be the last element, right? So that's 6. Boom. Look at that. So there are my 2 left and right parts. So the parts seem to be being broken down correctly. And one more thing we could try is, what if I don't start from the beginning, but I start from this negative 2? So P will be 1 then. And let's say I just want negative 2 to be by itself. So I leave, I set Q equal to 1 as well. PQ. And this is still 6. Now look what's going to happen. The left subarray is now empty. So why is that? Let's go back to the definition in our book. We were told that P can equal to Q. And in our pseudocode, how does the copying work? So here is the indexing. Notice. So we start from P, we go plus I minus 1. Why is that? Because when I is 0, when I is 1, excuse me, we're just copying, we copy over the pth element. And when I is n1, in other words, when we reach this last element here, then this just becomes q. So we copy over the qth element. So what we could do here is the following. Let's think this through. So again, for the left element, we want to start from P. We want to end with Q. Inclusive. So P needs to be there. Q needs to be there. So if P is 1 and Q is 1, right, we start from P. And we can go to Q plus 1. If I do this, what would happen? So if P were 1 and Q were 1, then this right index would become 2, and that element would be put, so 1 to 2. That single element gets put in the left array. Now, then we start from q plus 1 again, and we go all the way to the end. Okay, so let's see here. Let's see how this version does. So we define our A is, we first will do this case. So 0, 1, -4, -2, and then 0, 0, 1. It doesn't even look at 2 and 3. Why doesn't it look at 2 and 3? Because we said go up to the fourth element, right? What is the fourth element? 0, 1, 2, 3, 4. It is the 1. So that seemed to work. If I had said go to the end, boom, it now has considered those elements. Now, what if I said, I want you to start from 0, and I want you to end the q to be 0. In other words, I want the left subarray to just be the first element, and then go to the end. So everything else goes into the right subarray, and there we have it. Okay, so we start from P, we go to Q. Okay, and notice that P and Q can be the same because, for example, if P's were 2 and Q were 2, then Q plus 1 is 3. So 2 to 3 is that single element at index 2, which is what we want. And then we go from Q plus 1, from that element, last element, all the way to the end. And we're done. Okay, so that seems to work. Now let's just look at the edge cases. What if my A is, let's say, -3, and I say merge that, 0, 0, 6, sure. It tries to merge it. It tries to split it. There's nothing to split on the right. Why is there nothing to split on the right? Well, because P and Q are both zeros. So this just puts the 0th element in the left subarray, but then Q plus 1 is 1. So we're saying start from 1, go to 6, or whatever that last index is, but there's nothing at index 1. There is nothing at index 1, so it just returns you an empty list. Okay, so that seems to work. Our splitting works. Now, we managed to create 2 new copies. That's this part. That's up to line 7. All right, so now what we want to do is to each of them, we want to append this infinity. Now, there is a notion of infinity in Python, which is quite convenient, actually. So let's look it up. So we can say Python infinity. How can I represent infinite number? I'll look at that. Float inf or math inf. I guess this is nicer. Let's import math and pull math inf. So I'm going to import math here, and then to say append infinity to each of the sub arrays. Okay, so we'll say L append math.inf, R append math.inf. Here we go. Okay, so now we've completed up to line 9. So now this merging process begins. So let's understand how it begins before we begin coding it. So again, we start from the beginning, not the beginning of the array per se, but the beginning index we care about. So we start from there, go to the final index that we care about. Now we're comparing the element, we're comparing the ith element of L to the rth element of J. If left ones is smaller, if the left subarray's element is smaller, then we put that in this kth position into our original array. We replace the element of the original array with this element. Okay? In other words, we're starting to put the elements of the original array in their correct order, and we increase I. All right, so let's try that. First, we need 2 indices, line 10 and 11. These are the indices into the left and the right subarrays. So we could say the following. We could say I and J start from 0. Now remember, the book starts from 1, but that's because CLRS, or pseudocode in general, does not index from 0. This is specific to machines. So I and J start from 0. Now we can say for K in range from P, because that's what we care about, from P to R plus 1. Why R plus 1? Because remember, again, this is pseudocode, this is actual code. In actual code, the range generator, I believe, does not go up to the rightmost index is non-inclusive. If I had just put R here, it would go up to element R minus 1 and not to the element R. So I put plus 1 here, so it goes all the way to the end. So for K in this range, we have to compare the left and the right list. We say if the element in the left list is less than or equal to the element in the right one, what do? I put it in A, right? So AK equals this element and then append index. Otherwise, otherwise, in other words, if the right subarray's element is larger, then that's what we're going to put inside A. So we're going to say A at the kth index is the right one's element, and we increase that index by 1, J by 1. So, all right. So this should do our merging, and then I don't want to return anything. In fact, why do I not want to return anything? Because A is it's a reference to, it's a pointer to an object. We've been modifying the object itself. So when merge is done, it's essentially destructive. It's a destructive process. It modifies our array. So I don't need to return anything. Just the memory, whatever's in that memory location will have gotten modified. So let's take a look. Again, we launch Python. I will restart the process here. And let's make an A. Our A will be the same as in our example. So that is 1, 3, negative 1, 0, 7. There we go. And now I'm going to say merge A, start from 0. What do we want to put here? We want to put let's see. Yeah. So merge A, P to Q. So P being 0. I will make the left subarray 1, 3. So that's 0, 1. 0, 1 going to the left subarray. And then I want everything after that to be the right one. So that's 4. The last index is 4. We merge it. Let's take a look at A. Boom. Look at that beauty. It's now sorted. So as the algorithm states, everything's being merged correctly, and it relies on the fact that the left and the right subarrays are in order. 1 3 is in order. Negative 1 0 7 is in order. When we merge them, we get an ordered list. Notice that the merging function itself returns none. So in Python, when you return none, the interpreter doesn't print it. So the merge function itself essentially returns nothing, because we are not making a new list in which we put things in order, but rather we modify the order of the elements in the original list. This is called a destructive process. That's why later when I say print out this A again, I see those elements in order. Okay, so we have the merge function here. Now you could write all kinds of tests, etc., but we won't get bogged down in those details. So also, another thing to think about is that if we look at the pseudocode, notice how in pseudocode we actually have to they say what is the size of the left array, what is the size of the right array. Then these indices are cleverly picked to just accommodate this the loop up to the size. So we have to do this in more lower level languages, maybe like in C++, and C would have to do this kind of thing. Python is just amazing, right? I just say, here's a slice of my list. Here's a slice of my list. I mean, I'm not even using the loop here at all. I mean, I am under the hood. Well, no, I'm not. There is no for loop here. So it's much shorter, much sweeter. The only for loop I'm using is here. And even this part, right? If you're a Python, if you're a hardcore Pythonista, you could completely avoid this loop as well. But I want to follow this pseudocode as closely as I can. So that's our merge. Now, let's think about how many steps it takes. We already talked about this, but let's try and go through it. So each time through my loop, let me open this picture here. Each time through my loop, through my merging process, what do? Each time, one of the elements from the left and the right subarrays, from the left and the right subarrays, each time through the loop, one of the elements gets crossed out and put into my original list. When all the elements have been crossed out, the process will stop. Right? When all the elements get crossed out, I will have gone from P, from my starting index, to R, which is my last index that I care about. In other words, I will have looked at all the elements. Let's repeat that statement one more time. Each time through the loop, one of the elements in the left or right subarray gets crossed out and put into the original list. Okay? And when I've looked at all of them, my process ends. Well, how many operations is my process? Then my process, the number of operations that I have to do is the size of the left subarray, which we'll call NL, plus the size of the right subarray, which we'll call NR. Approximately, right? So this is the time of my process is approximately this many steps. Now, n sub L plus n sub R can at most be the size of my original array, because that's where the splits are coming from my original array. Now, let's call the size of my original array n, and just n. That looks like an M. It's an n. So the time it takes for merging to complete is going to be less than or equal to n. Okay? Maybe some constant here, but less than or equal to n. So we'll call this process big O of n. It's a linear time algorithm. Okay, the number of steps I'm going to have to take to merge two subarrays is at most the size of the original array, which is n, and so the time it takes is at most n, big O of n. So it's a linear time algorithm. Back to the book. Now, the second exercise I think will be illustrative is if we now try, let's see, if we now try to implement the same thing in C, just so that we're not completely bound to these higher level constructs that Python provides us. For example, notion of infinity, right? This is Python gives us to us, but how do you do this in C? How do you put in a number that you can be sure is going to be larger or equal to anything else? And C certainly doesn't have this list thing where or slicing like this. So we don't want to be bound to these constructs. Okay, so let's go here. So this is going to be the same function, but in C. Now, one thing we're going to do, well, first let's define our function. What does our function do? Our function does not return anything. It's called merge. It takes in an integer array, a list of integers. So int, let's say A. It takes starting index, it takes the index at which we stop the left subarray, and it takes index at the end. Now, I'm assuming you know how a pointer works. To be honest, I haven't done C coding in so long. You probably saw me just now try to do the array notation in C, and I can't remember whether it was like this, the array brackets go after int, or if they go after the name. I'm pretty sure they go after the name. You know what? I'm gonna look this up right now. Let's see. So let's say C function array argument. Let's see, passing arrays to functions. That's what we want. Yes, seems the brackets go after the name. All right. Oops. So that is nice, but I'm going to stick to the pointer notation. Why? So this is going to be a little bit of my own opinion. My opinion is if you're coding C, you you want to do things the way the machine does things. You don't want extra layers of abstraction. For example, I mean, we have these functional languages. We have things like Haskell, etc. And just functional approach is just beautiful. And if you're coming from math like I am, it just makes sense, right? It's essentially you're doing functional composition on a very large scale. The problem though is at some point you understand that this is not actually how the computer does things really. This is this is a idiomatic way that you code to make things simpler for you, or maybe for the reader of the code, but the machine is actually not doing things this way. And if you're coding in C, the I mean, my understanding is that you want to code close to how the machine does things so you can optimize it. And how a machine does an array. So when I say this is incredibly close to having a pointer, creating some memory block, and just moving your pointer through the memory block. Okay, to me personally, I tend to think of an array as just an abstraction over the pointer. That's just me. Okay? So I'm just going to use the pointer here. Let's start defining our function. So merge. Let's take our array, take our PQR. See what we can do here. Let's open our pseudocode. So first thing we need to do is we need to define the size of the left and right arrays, right? So integer n1 will be q minus p plus 1. And n2, so q minus p plus 1, right? That's exactly the number of elements from q to p. And then here we'll have r minus q. That's the number of elements between r and q. Okay, so now we need two subarrays. We need to make two subarrays. How can we do that? Well, we need to allocate memory, right? We need to allocate memory for those two subarrays. So how do you allocate memory in C? Well, suppose you don't remember. Let's go. How to allocate memory in C. The dynamic memory allocation, malloc. Okay, yeah, there it is. So what I want to do is I want my left subarray. This is going to be, I'm going to allocate, how much memory do I want to allocate? Well, this is going to be integers, so size of an integer. How many integers do I want? I want n1 of them. Now, remember this returns pointer to void. This returns a void pointer. And all that really means is that if I want to go from the block in the memory where I'm currently pointing to the next block, then this process doesn't really know what the jump size should be. How large is my each block? Okay, how many memory cells do I need to jump in order to complete a block? And the way I specify that is I say you are an integer pointer. In other words, the block is the same size, okay, as an integer. So when you jump to the next block, you need to jump the same number of bytes as what an integer is. So it'll do that jump there. Now we'll do the same thing for the right array. It'll be a pointer. We'll allocate our memory. And this will have the size n2. Okay, what do we do next? Next, we need to append an extra thing to it. Right. So we don't want size n1 and n2. Actually, we want n1 plus 1, n2 plus 1, so that we can put the infinities there. So let's do n1 plus 1, 1 plus 1, and n2 plus 1. Okay. So now what I want to do is I want to loop through my array and fill up the left and right subarrays. Okay, so let's do that. So for integer I equals 0, and we'll say I is less than n1, I plus plus. What we're going to do is we're going to say L, Li, you just follow the pseudocode. Li here is, into this left subarray, we're going to put the element from the A that is at position P plus I minus 1. So that will fill up these values here. Now, again, notice how I'm using this array index, the array notation. This is perfectly fine. In fact, most people will probably prefer this. But if I'm coding in C, and again, I'm thinking of arrays as abstractions over pointers to memory, I would rather use pointer arithmetic. Now, I've forgotten how to do that. What do? I Google it. I hope you're picking up something from my learning experience here, is that you should learn how to Google stuff. So pointer arithmetic in C. Let's see, pointer arithmetic. Here's my pointer. Move. Okay, so if I plus plus, we jump to the next block. But how do I set the value there? I think I put a star. I think I have to dereference the pointer and then do that. In fact, I'm pretty sure. Yeah, value star PT. Yes. Okay. So I have to dereference the pointer. So the way I do that is I will say dereference the pointer. So in the value that I'm currently pointing to, put this value, right? Put this value, and then you can jump your block to the next memory block, to the next block in the memory. Okay, let's do the same thing for the right one. So j less than n2, j plus plus. So now we will say star r equals, we dereference the pointer. What element do we put here? Well, we put a, so we're starting from q, right? And we plus the j. And this will take us all the way to the end, plus the j. There we go. Q plus j. And we jump the block. There we go. Now we want to put infinity, right, at the last position. So what is the last position? Here, when I becomes equal to n plus 1, I want to put this notion of infinity. Now in C, there's a notion of infinity, obviously, but there is this notion of integer max in C. So it's this the highest values of my integers. Right now, I'm assuming that we're going to be dealing with integers. So I have this notion of int max. No, I don't want my MSDN. I just want regular C. So here it is. C has this header file called limits.h that we can import or include. And in it, we see this int max constant. There it is. So we'll use it. So we'll include limits.h. And then, so here, we'll dereference L one more time, and we'll set it equal to int max. And here we'll dereference pointer to R one more time. And we will set it equal to int max. There we go. So these are my notions of infinity now. infinities in there. So now it's time to go through the merging process again. So we start from P. Now notice I'm closely following this the pseudocode in the book, but again I remind you that the book starts indexing from 1. So we might need to adjust these indices later on, but this is, we'll go through it in a minute. We're just putting down the general layout first. So let's do the merging process. So we'll say for integer k starting from p, k less than r plus 1, because we want to go all the way to the end, plus, what do I want to do? I'm saying if, I need my I and j indices, right? These I and j indices. So integer I equals 0, integer j 0. In fact, as I'm thinking about, I'm thinking whether I really need them if I'm doing pointer arithmetic. Let's try this. Let's do this. So I'll say if reference L, where is this? Okay, so now I immediately see an issue, and here's the issue. The issue is that I created the pointer to the left and the right subarrays, but then I've been moving that pointer to the right. Essentially, I've lost the pointer to the starting element in my sublist, in my subarrays. I've lost the place, right? Because I've been moving L around. So maybe what we ought to do is when we are looping here, we also create a pointer that points to the same place as my list. And then instead of moving, let's see. And then instead of moving L, I can just move P like so. I wonder if this will work. And we can say in start Q equals R. And we'll dereference Q and put the L. Oh no, we already have Q. Q is taken. I believe P is taken too. Yeah. All right. So we'll call this Z. We'll call this W. This will be Z. This will be Z. This will be W. And this will be W. And this will be Z. And this will be W. So essentially, the reason we did this is because we are now, as we go to the right, we're moving the pointer called W that has the label W. R and L are still pointing to the beginning block in memory of our left and right subarrays. So now as we start our comparison, I'm saying the reference L, and remember L is now still pointing to the beginning. So the reference L, and if that's less than or equal to whatever you get when you try to dereference R, and what I want you to do is in the kth position of A, I want you to put that value, and I want you to jump to the next block in L. Otherwise, I want you to put in that position whatever you get when you dereference the right subarray, the value in the right subarray where you're currently pointing to, and then jump to the next block of the right subarray. All right. Now, again, not the prettiest looking code by any means. The point is for now to get it working. So let's go through our example here. Let's make sure the indices work, etc. So I come back here. What did I have? I had 1, 3. So let me scroll a little down here. I had 1, 3 as my left one. And then as the right subarray, I had negative 107. Negative 107. Okay. So P is 0. Q is 1. And R is 4. Now let's see how things work. Let me open Sublime here. All right. So N1 needs to be 2 because I have 2 elements, right? Q minus P plus 1. Q is 1. P is 0. That's 1 plus 1. That's 2. Good. 2 elements. The rest should be, the rest of them should be here. So R is 4, and 4 minus 1, right? 4 minus 1 is 3. And that gives me exactly 3 elements. Good. So that's correct. So we make our left and right subarrays. We create the pointer pointing to the same block as this subarray L. And what do? We're saying, okay, when I is 0, notice here, okay. So when I starts from 0, what element am I picking from A? I'm picking P plus 0 plus minus 1. That is the P minus 1th element. That's not what I want. I want the Pth element. So essentially, what I should do is get rid of this minus 1. So when I is 0, I'm getting the Pth element, not the P minus 1th element. Okay, so that element gets put in the block where Z is pointing currently to, and then we jump in memory to the next block. And when this process ends in the final block, we put this notion of the largest of infinity, essentially, the largest value that's coming from this limits.h. Then we do the same thing for the right one. Okay, let's check again. So when j is 0, then I'm essentially putting the qth element. I don't want to put the qth element, right? The qth element is part of the left subarray. So what I want to do is I want to put the q plus 1th element. So where I want to start from. Again, when j is 0, so q, or maybe we can start this from 1. So when j is 1, is that right? I don't think that's right. Let's see. So when j is, so in this case, j is 0, and 2 is 3 in our example, right? What is q? Q is 1. So when j is 0, if I did q plus 1, I'd do this element, right? Then j would become 1, and I'd get this element. Then j would become 2, and I'd get this element, and then j would become 3, and we'd be done. Yeah, that works. Plus 1. You would get a segmentation fault, and it's absolutely no help, but we'll try it out. So then we start from P. That's our initial place. We go all the way to less than R plus 1, right? Because I want to include the last index as R in my computation. So I say less than R plus 1. You could always say less than or equal to R if you want. Better. Let's leave it at less than R plus 1 for now. So we dereference, we compare. If the left element is less than the right one, that's what we put in our list. We jump to the next block. Otherwise, we put the right subarrays element in our list, and we jump to the next block. Okay. So let's try to use this. And I actually don't know if, well, let's see. So yeah, this, I think this malloc creates memory on the heap, so I'm going to free it before people shoot at me. So I free the memory here. I free the memory here. There we go. These are temporary, right? I don't care for these. I care for the modified A. So let's make our A. This will be a pointer A equals, let's malloc some amount of memory to this guy. How much memory do we want to give it? Let's say 3. 3, no, not 3. How many did we have here? 5. Let's do this example here. So 5 elements. 5. And I want this to be an integer pointer. I want the jump to be the same number of bytes as an integer. So now let's start filling in the values. So we'll say for integer I is 0, I less than 5i plus plus. That's the way to do it. Yeah, sure. So the reference, I put specific values there. Yeah, I want specific values, so I'll just do this. Integer a equals, I think I'm allowed to do this if I remember correctly, 1, 3, negative 1, 0, 7. There we go. If I can't do it, it'll yell at me. So then I'm going to merge a. So 0, 1, I'm going off of this bottom example here. P is 0, Q is 1. And R was 4. And so now I'll just print it out and see how everything goes. So for int I is 0, I less than 5, I plus plus. We'll print f. We'll print f an integer, space after it, and this will be a subscript I. So now I have a mixture of stuff going on, right? So here's some error. This is like to see to use both maybe. Here's an array notation for iterating through this memory block, and here's pointer notation. Personally, again, this might sound strange. Maybe it's error prone for some people, but for me, it's just easier to think about this whole thing as a block of memory. It's weird. People love abstractions. And maybe it's because I'm a terrible programmer and I just don't understand the value of, or I do, but maybe not to a point that a professional software engineer understands the value of abstraction. But coming from my background, is just I love to break things down into their atomic constituents and just understanding things at that level, okay, from the building blocks. And because I understand, okay, here is a memory block, I allocated memory block here, and I'm just putting things in this memory. It's just easier for me to think in those terms, and as I move through the memory block and I change the values in that. That's it. So that's why I like this pointer notation, is because I'm just working with the atomic, the atomic unit, as opposed to these abstractions, which is the reason a lot of the times I end up shooting myself in the foot. But hey, okay, so let's give this a go. So we're going to try and compile this. Naturally, of course, it's not going to compile. Did I not save this? I saved it in the wrong place. Okay. Let's see. Move this guy out of here. It'll go to CLRS. We'll toss it here. Okay. Now, naturally, this is not going to compile, but let's see what it says. Okay. Declaration of malloc. Oh, yeah. Malloc was in some library, right? Okay, let's see. Where were you defined? Malloc. Plus reference. Malloc is defined in stdlib. stdlib, ladies and gentlemen. Include stdlib.h. This another go. Let's see. Expected identifier, or does C not let me do this? Does C not let me define two variables? I'm sure it did. What is the problem here? Let's take a look. How to define two variable, or define initialize how to define two variables in a for loop. C. Two variables in a for loop. C. I just love Google. It's like the thing is reading my mind. Yeah, except these are not at all what I was looking for. Okay, so size. So it seems like if they're the same type, he does it. Maybe. Two variables of different type. Is it possible of different types in a for loop? Not possible. Yes, but you can do this. Okay, fine. Fine. So what that means is I'll just declare here int star z, int star t, w. And I'll just say what they're equal here, and I'll just say what they're equal here, and that should take care of that. All right, next. W undeclared first warning implicit declaration of function free. Lib free. Let's see. Clear the screen because I have no idea what's going on at this point. Okay. Implicit declaration of function. Does the stuff from stdlib not get linked? Let's see. I might need to link it explicitly. See, do I need to link stdlib explicitly? Why do I have to link the math library? Yes, the math library you do. Okay, sometimes it actually helps to write out the warning. So the first warning, implicit declaration of function malloc. C. Implicit declaration of function malloc. Why do I get warning every time I use malloc? Okay, you need to add stdlib h, which we did, right? stdlib.h, there it is. Oh, of course. I still have the file. The file that I have open is the file in the old location. I don't want this file. I want this file. All right. So let's include this stdlib lib.h. And then we had to pull out the declaration of these pointers in pointer z and w. And then we can say that z was L and then w was R, like so. And now let's try this again. Clear the screen. Okay. Makes integer from pointer without a cast. L is an integer. Pointer makes integer from pointer. Oh yeah, these are the same types, aren't they? Yeah, it assumes that z, I guess it assumes that z will be an integer too. All right, fine. We'll just do that here. Z equals L. And we'll say that W equals R. I'm sure you've realized at this point that this is a learning process for me too. You're going through my thought process here. This is not a colon, it's a semicolon. Okay, compile. Makes integer. Okay. Let's see here. W equals R. Error. I undeclared. Where do you see an I here? Okay, this is a J. Compile. Oh man, it compiled. Okay, let's try to run this. So, okay, a.exe has stopped working. I just love C. Okay, so I'm guessing this is this is the Windows version of a maybe like a segfault. I'm this sounds to me like we're trying to access a memory we don't have access to. And this is exactly the pitfall of using the star notation is you mess up a lot unless you know what you're doing, which I don't. As you can tell, Python is so much cleaner and easier for this kind of stuff, but we got to learn. Okay, we have to learn. We don't get better if we don't learn. So let's see what the issue is. Did we allocate enough memory? Well, we allocated enough to accommodate our infinities, right? So one way to step through it is let me comment this part out for a second. I'm gonna comment this. And all I'm gonna do is I'm gonna say here. And the reason I'm gonna do this is that I know that wherever that like the restricted memory block access that happens, it's not before this part of the code. So let's see. Compile. Do I not have stdio? I do. Why are we complaining? Oh, yes. C strings have to be double quoted, unlike Python. Compile. Let's run our exe. So that works. I was able to print it. Now notice that I have not changed anything about A because changing the actual merging process happens down here and we haven't done that. So this part of the code seems okay. In fact, I could say print an integer and I want to see what currently Z is pointing to, or Z. And if everything goes right, I should see the maximum integer there. And I do. There it is. So this pointer Z is not crashing. It's not accessing any memory location to which it doesn't have access to because we've allocated enough memory. It's fine. So everything up to here is good. We're ready to move on. So problem is somewhere here. And in fact, I'm willing to bet that the problem is in this for loop, in this block. I'm not quite fond of this indexing. So let's try to put a print statement here. See? In fact, instead of here, maybe I'll just put, maybe I'll just do what I just did before. I'll try to write out the value that we're currently, the value in the memory block that we're currently pointing to. And if this does not crash my code, then I should again see this int max value. Let's compile. And let's see what we get. GCC, no, not Python, a.exe. And I do see it. There it is. So that didn't crash my code. So that's fine. Even though, again, this kind of looks, oh man, this doesn't look, maybe I should use +1 J. That putting the +1 after the J, it makes it seem as though that +1 is part of the computation with J, when in fact it just says start the indexing from Q plus 1th element. That's all it says. So yeah, 1 there is better in my opinion. In fact, I would even go as far as to put parentheses around this. Clarify that there's no computation being done with that +1. It's just there to signify the index, starting index. All right, so now we know where the problem is, though. The problem has to be in this loop, then. It's in the core merging loop. Make sure I'm going to compile one more time and run it, and it crashes. Yes. Okay. So we're starting from P. We're going to R plus 1, K plus plus. Let's go here, and let's see if this dereferencing is working correctly. I want you to dereference whatever I have in L, and then dereference whatever I have in R, and tell me what those values are, please, as you loop through it. Or you can, let's print is Python. It's print F in C. Okay, fine. All right, so look at that. So we got 1737. Let's open our example here. Where is it? Here it is. 1737. 7. Hmm. Well, that looks strange, doesn't it? Why are we pointing at 7? We should not be pointing at 7. We should be pointing at -1. It should be 1, -1, not 1, 7. Oh, excuse me. Excuse me. This we only. Oh yeah. Let's copy this print case over here too. Notice the reason it said 117 is because the only place where I put the print statement is when the value in the left subarray is less than or equal to the value in the right subarray. And the first time that happens is when the value in the right subarray becomes 7. It's the first time when 1 is less than or equal to 7. So that's the only time I get printout. So let's try this again. 173. Did I not just save that? I'm sure I did. So is the problem here? Oh, run. Okay. So 1 minus 1 is my first comparison. Good. Let me open this here. 1 minus 1 is my first comparison. Then 1, 0. Then 1, 7. Then 3, 7. Then this max integer 7. Right? Max integer 7. In which case, the value in the right subarray is smaller than the value in the left subarray. And it puts it in this kth place. So what the problem is that I think we're overstepping into one memory block. So this line, we might be overstepping. Let's check our loop conditions again. How large is our array really? Okay, so if P is 0 and R is 4, and I say go from 0 to 5, well, of course. Okay, so notice that P was 0 and R is 4, right? The last index, the first index in my array is 0, last index in my array is 4. When I'm doing the merging process, I am saying start from the 0th element of it. It's keep track of the index starting from 0, going up to R plus 1, not inclusive. Now R was 4, so R plus 1 is 5. So this is gonna the last place where it should be inserting anything is index 4, which I do have. My array is of size 4. Let's see. Is it this line? I think it's this line. I think that's R plus 1. This last time. So when it puts the 7 into my array and goes over to infinity, let's check. So you know that's probably not it. Let's run it nevertheless. It does print that last here, and then it crashes. So at this after this last point, both values. Let me print R through the loop. I kind of want to keep track of these things. Let's see. What is the value of P? So we'll say P equals, and then we'll say R equals, and then we'll say K equals. We'll put PRK here. This helps me keep track of the indices, that the indices are um, moving correctly. We run it. Okay. So R is 0, as it should be. 0, 0, 0, 1. Let's see. 0, 0, right? 1 minus 1, 0, 0. Then 0, 1. Then 0, 2. Then 0, 3. Yeah, K goes 0, 3. Hmm. 0, so 0, 3, that 3 set. So whenever K is 3, we're doing this comparison, 3 and 7. So obviously 3 gets tossed in there. When K becomes 4, we're doing the comparison between integer max from the left subarray and 7. So 7 gets tossed in there. Right. Seven gets tossed in there. And then it increases by 1 over to its integer max. The loop comes back to the condition. K becomes 5. And then it should stop. Let's see. Okay, that's weird. So that worked. Freeing is the problem. Why? Why is freeing the problem? So here's what I'm thinking. When we allocated the memory and then put the pointer in this variable L, over here when we're doing the merging process, we're actually moving that pointer. And then what I'm trying to free is the last block in that chain, in that memory chain that I'd created, the block of size n1 plus 1 and n2 plus 1. The last block, essentially, where the infinities are, that's what I'm trying to free. Now, I'm not by any means versed. I'm going to learn this. I'm going to get to it. But I seem to recall reading somewhere that you can only free a memory block. We'll call it the blockchain. But you can only free a memory blockchain if you specify the starting point of that blockchain. In other words, the starting point where you had first created that memory blockchain from that memory block. That way, if my assumption is correct, then we would need to do the following. We would need to say reassign Z to L again and W to R again. And then instead of moving around L and R, you move around, you reference Z and W, and you work with those. You move those around, essentially. ZW, and we're gonna move those. And now I should be able to free LNR because they're pointing to the beginning of that blockchain. Let's run this. How would you look at that? My assumption was correct. So it seems, let me draw this out. It seems that when you assign a memory block, so you called your malloc, right? And let's say you wanted a memory block of 4 integers. So you called malloc here, and you assigned this to some variable L, and you did the same thing, created another memory blockchain of 4 blocks. Here's my blockchain of L, here's my blockchain of R. Now, when so you have pointers, right? So yeah, maybe this. Let me erase this, because these arrows, I'm actually planning on drawing a different thing. So L essentially initially is pointing to this first block. So is R. Now what I'm doing is, because I'm doing pointer arithmetic here, I'm saying put some number in this block and then move the pointer over. Now this pointer is gone at that point. Put some number in this block, move the pointer over. Blah, 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 right? Now, if I say free this memory, this blockchain, free it from memory, then it seems that the free function wants to know where was the starting place of this blockchain when I had created it. In other words, it wants to know the address of this guy, but I don't have it. I'm pointing to this guy. The address of this is lost. So essentially, it seems what we want to do is we want to keep L and R always pointing to this beginning block in the blockchain. And then just if I want to traverse the blockchain, then I make a copy pointer, a pointer that initially points to the same place as L. But if I want to move it around, I can. We'll call this pointer P. I'm moving around P, but L is always pointing to the beginning. So if I now say free L, free this point, whatever this pointer is pointing to, it's pointing to this initial block in the blockchain, and so it can just erase the whole blockchain. My guess is that this initial block holds some kind of information as to how big the whole blockchain was when you created, like what was this amount in size of that you had specified, so it knows it should clear out that whole thing. That would be my guess. Okay, so that's the code in C. Whew. Man, that was, as you saw. Again, I'm not well versed in C by any means, but I mean, yeah, I'm practicing, I'm learning. Hopefully, by the end of this algorithm session, I will be pretty good at it. But as you can see, there is a lot more things to take care of, a lot more pitfalls compared to this beauty here. I mean, look at this. It's just exactly the pseudocode. Whereas here, there's quite a lot to do. Now, I'll leave it to you to sort of try and rewrite these two things, and then try and do try and time the two programs and see how big the difference is. I would suggest making A quite large, the array, okay? Because then the difference might be more striking. All right. So that's our pseudocode implemented. That's our merge implemented in C and Python. So I will do here's the pseudocode for merge sort. As you can see, it's absolutely tiny. And in Python, it's literally it's exactly this. You just write this in Python. So I'll leave it up to you to finish the implementation of merge sort here. And then we'll pick up with the analysis of the recurrent algorithms, of this divide and conquer algorithms next time, how we analyze the time complexity, how long it takes formally. It's a very useful skill to have, because a lot of times if you're interviewing for a position, you might get asked some question where runtime of a recurrent algorithm is important. And a lot of times people, they do some guesswork. They're saying, okay, at each step, I seem to be doing two things. So, at each step, it doubles. I have n steps. So that's 2 to the nth power. Okay. Yes, but sometimes there's more than just doubling. The number of operations per step may not be the same, because there might be some conditions, etc. So you want to be able to do one formal analysis of the recurrent algorithm, the time it takes to complete, which is what we'll do next time. So I urge you to try what I just did yourselves. Okay. Try going try implementing these two things, these two algorithms, or this algorithm in a language of your choice. I'm gonna keep doing it in both Python and C because I see the value in doing both of them. Okay, Python is fantastic. I absolutely love this language, but I also see the value in knowing C. It's truly. I mean, if you're gonna build a large system or some large application, I see the value. And personally, I love the fact that I get to work, that I get to actually instruct the computer to operate the way it operates by allocating a memory block, by stepping through it, etc. I mean, I love understanding it at that level. I mean, if you hate it, then you might as well just go to Python directly. All right. So we'll pick up with formal analysis next time. Have a great weekend. Later, guys.